So we're going to talk about the normal model next, all right? And so I want you to realize what we talked about up until this point. We have talked about, when we talk about probabilities, there are two distributions in particular that we focus on in a introductory class of statistics. And that's the binomial distribution and the normal distribution. All right, those are two distributions we really focus on. The binomial we covered is that we covered in our last unit and on our last test. And the binomial says that for the binomial is a discrete distribution, which means that everything in the binomial has to be a whole number to calculate, right? And so we saw how to calculate that by setting up a table and you can write in the probabilities for that, right? So you had to be at a number. The normal model is what we call a continuous. Continuous. Remember, there's two types of quantitative variables. They are discrete, which are whole numbers, and there's continuous, which is a measurable or a partial part of something, partial of something. So the normal distribution is used for continuous data. And when you have continuous data, you can't draw tables anymore because there's no longer a such thing as an exact value. And what you're going to do for this particular distribution is it's a function that we're going to calculate. And it's really going to be, we're going to find actually, we're going to graph it and draw curves. And we're finding area under curves, all right? That's what we're going to do essentially, find the area under the curve. The problem with finding the area under the curve, that is a calculus concept. That's essentially what calculus is finding areas under the curve. Most of you have not taken calculus and do not know how to integrate, but that's okay because Excel will do all the integration for you, all right? So we're going to start off with the normal model. Here are the learning objectives. We talk about the properties of the normal distribution, find normal probabilities, talk about sampling distributions in our next unit, and central limit theorem on next unit too. Normally I would do this activity, but we're going to skip over that. We're going to talk about this. So here are the properties of a normal distribution. The distribution is continuous. It's continuous. All right, that's the first thing. So we use this for continuous data. And the shape of the distribution is bell-shaped, unimodal, and symmetric. Let's talk about what all that means. In particular, bell shape, you know what bell shape means. That's just looking at a bell curve or looking at a bell. But the other things that we talk about, we call unimodal. The word unimodal in terms of statistics means you have, when we talk about unimodal, just this means that you have one peak. You have one peak. That's what unimodal means for us. And then anybody can remind me what symmetric means? Symmetric is a shape. Can anybody tell me what symmetric means? What's the shape?
Equal on both sides.
So keep going though. How do we define shape? There was left skewed, right skewed, and symmetric. What do you know about a left skewed distribution? What do you know about a left skewed distribution?
Positive?
Okay, that's what it is. It's negative, actually. It's negative. But what do you know about it? What do we know about, in particular, what do we know about the mean and the median?
The mean is less than the median.
Good. The mean is less than the median left skewed. What about a right skewed? The mean is greater than the median. In a symmetric distribution, what do you know about that?
They're equal.
They're equal. So here's what this really means. The mean and median are equal in this particular distribution. The mean equals the median. In this particular distribution, the mean is at the center of the curve. So when we look at this, we call the mean mu. We call the mean mu. The Greek letter mu. Have we talked about that before? I feel like we have. If we haven't, okay, if you've never seen it, that's the Greek letter mu. So this just is the Greek letter mu. And it stands for the population mean. It's the population mean. And that population mean is going to sit at the middle of this curve, like that. There are 6 standard deviations underneath the curve. I know we talked about that because we talked about that in the empirical rule. But in case you forgot, there are a total of 6 standard deviations underneath this curve. There are 3 standard deviations to the left, and there's another 3 to the right of the mean. So essentially what you get here, from here to here, is 3 sigma. From here to here is also 3 sigma. So the total number, though, is 6 sigma. 3 standard deviations to the left, 3 standard deviations to the right. The total number is 6 sigma. There's 6 standard deviations underneath the curve. If I look at this, I can ask you what is the standard deviation of this particular curve. You should be able to tell me that. You should be able to tell me that. What's the standard deviation of this curve, by the way? Can you tell me? Can anybody tell me what the mean of the curve is? What's the mean of the curve?
30.
30. What's the standard deviation then?
5.
Thank you. So mu is equal to, in this particular distribution, mu is equal to 30 and sigma is equal to 5. Do we see how we got that? Mean, center of the curve, Standard deviation, there's 3 to the right. These are all increasing by 5, so the standard deviation is 5. 3 to the left, these are all decreasing by 5, so the standard deviation is 5. All right, so that's what we're doing with this curve. The next thing is, because it's a continuous distribution, the tails of the distribution are asymptotic. What does the word asymptotic mean? That means they form asymptotes with the horizontal axis. They will never touch the horizontal axis. As a matter of fact, they will extend forever. They extend forever to the left and to the right, meaning that on this side, this distribution goes up to negative infinity. And on this side over here, it goes up to positive infinity. So the tails will go like this. Now, here's why this is valuable to us then. Because this is a curve, and because it goes from negative infinity to positive infinity, what we're going to do now is associate this curve and the area underneath it with probability. And what I mean by that is the area underneath this curve is going to be represented by 100%. So this is a 100% of the data sitting underneath the curve. And what happens now is I can find values or probabilities. I can find probability because the area, if it's 100%, is actually equal to 1. It's actually equal to 1, and 1 is 100%, by the way. So the area equals 1. Remember, when we add up all the probabilities, when we sum probabilities, what do they add up to? When you add up all the probabilities, what do they always add up to? Anybody tell me that? 1. They always add up to 1. So it's the same concept, right? We're applying that concept here. The area equals 1, the probability sum up to 1, so we can do that. So here's how it's going to work then. I should be able to find at any particular value, up to any particular value, the area that is calculated up to that value, right? So for instance, if I ask you to find the area up to the mean, how much data is up at the mean? How much data is up to the mean? Can you tell me that?
Half.
Half of it, which is 50%, right? What else do you know about the mean in a normal distribution? It equals the what?
Median.
What does the mean equal? It equals the median. And we know that median marks where? Where does the median mark? The median marks the 50 percentile of data, or the half mark of the data. Do you understand that? So this is all coming back together. So here's an example. For these 4 different curves, I want you to notice something about all 4 curves. All 4 curves are bell-shaped, unimodal, and they're also symmetric, which means that they are all normal curves. Do we understand that? These 4 curves are all normal curves. My question is, what makes these curves different? What is going to make these curves different? Can anybody tell me that? Do they look like the same curves?
No.
This
No,
standard
they have the same
deviation.
shape, but what is making them different? Somebody said it. Go keep. What did you say?
Standard deviation.
What else? That's one thing that makes them different. What else makes them different?
They're medians.
They're not the medians, but they're
Mm.
means. Their means make them different. So first question says, what is the mean of each curve? If I want to find the means of these curves, what is the mean of curve A?
-2.
Thank you so much. So curve A sits here, and mu of A is equal to 2, -2. What is the mean of curve B?
0.
What about C?
0.
What about D?
0.
Thank you so much. So mu of B is equal to mu of C, which is equal to mu of D. And they're all equal to 0. They all have the exact same means. Now, because they all have the exact same means, then what makes them different? What makes these curves different? They all have the exact same means. What make them different?
The deviation.
Standard deviation. So mu of A is equal to -2. Mu of B equals mu of C equals mu of D, and they all equal 0. So we're saying now that the standard deviation is what makes these curves different, right? Because the standard deviations are different, the curves look different. I want to know this then. Remember, what is standard deviation? Does anybody remind what standard deviation is? What does the word standard mean? Standard in statistics, what does that mean?
Normal.
Normal, or it means average. It's an average. So what is a deviation? How far you're away from the average. So this is the average deviation away from the mean. That's how we say the standard deviation. It's the average deviation away from the mean, right? Now, I want to know which curve has the smallest standard deviation, or the smallest distance away from the mean. What curve is that going to be? A, B, C, or D?
B.
Why
B.
B? Why
Because
curve
it's
B?
the tightest.
It's the tightest, which means that you're packing more data inside of a smaller interval. So in this particular case, curve B has the smallest standard deviation. Which one would be next, by the way?
A.
Can you tell me which one? A. So curve B is less than curve A. Which one is next, by the way?
C.
C, which is less than curve C. And the last one would be what?
D.
Curve D, right? So which curve has the largest standard deviation? Curve D. Why does D have the largest standard deviation?
Because
It
it's
is
the
the
flattest.
good. It's the most spread out. It's the most spread out. All right. Curve B has the smallest because it's the tightest. So right there, all we've done so far is we identified different curves by their mean and their standard deviations. Here's another example. I want you to estimate the mean and standard deviation from the graph. Estimate the mean and standard deviation from the graph. The mean is always going to be an easy value to find because the mean sits where at?
In the middle.
In the middle. So what is my mean going to be equal to here? What is mu equal to?
0.
0. Thank you. The mean mu is equal to 0. So the mean of this curve, mu, when you look at it, is equal to 0. Now, if you had to guess the standard deviation, what would the standard deviation be?
20.
Well, that 20, technically, the values are actually falling about, right? Here's the first standard deviation on both sides. Here is the first standard deviation, second standard deviations are about here. Third standard deviations are about here, way out here. The scale's not drawn very accurately, what I'm telling you. But here's what we do know.
So like,
Here's what we do know. Keep going, I'm listening.
would it be 33 because it's like 100 divided into 3 sections?
Great job. Great job. That's what I want you to get at. Good. So we know underneath this curve is how many standard deviations to the right?
3.
3. That's 3 sigma to the right, right? How many are to the left? It's also what? 3 sigma, right? There's a couple ways you can do it. We can look at it in terms of to the right from 0 to 100 is what? That's just 100, distance of 100, right? So I want to calculate sigma. Sigma is equal to 100 divided by 3. Why am I dividing by 3?
Because there's 3 deviations.
3 standard deviations. Where does 100 come from? That's the distance from the mean to the very end of this data set. So we divide 100 by 3, we get 33.3. Gianna, great job on that, by the way. Most people don't pick up on that. Another way to do that is to know that how many standard deviations underneath this curve total? How many are underneath there total? 6 standard deviations, right? We know that the distance from this end, or the range is what I'm actually calculating. The range from this point to this point, well, from here, negative 100 to 0 is 100. And then from 0 to 100 is another 100. So that's 200. So another way to do this would have been to do 200 divided by 6, which is also 33.3. So the best estimate for the standard deviation here is going to be 33.3. All right. Anybody have any questions on that? All right. So what I want y'all to pick up on right now is that where does the mean sit at?
In the middle.
In the middle. The mean sits in the middle of the normal curve, right? How are the normal curves different from each other? Well, they all have different means and they all have different standard deviations. So what ends up happening is this then. Because every curve has a different mean and has different standard deviations, and there's an infinite number of curves out there, then we define these curves. We define these curves based on their means and their standard deviations. So when I write that, these are what we call the parameters, by the way. Do y'all know what parameters are? Not all y'all speak up at once. Don't worry about it. They're the population values. Good. They're the population values. Parameters are what we call population values. And in a normal distribution, your population values are going to be your mean. You define it by the mean and the standard deviation. And what that means is that if I know the mean of this curve and I know the standard deviation of this curve, I can draw any one of these curves. If I know the mean and the standard deviation, I can draw any one of these curves because I know where I'll put my mean at. Where do I put the mean at?
In the middle.
In the middle. And I use how many standard deviations to the right?
3.
3 to the right. And then how many to the left?
3.
3 to the left, right? So based off of that, then this becomes a problem when we try to compare things. When we try to compare things, if they have different means and different standard deviations, it's hard to compare distributions. So what they've created, or what we found, is using a transformation, we can get everything back down to what's called the standard normal. And again, the word standard means average. So a standard normal is the average normal curve. It's the average normal curve. All right. And in the average normal, we use the variable z. And this is where we get z-scores from. We use the variable z. And we say that z follows a normal distribution. Every z curve has a mean of 0 and a standard deviation of 1. So if you look here, this curve is sitting at 0. And then the standard deviations are 1, 2, 3. -1, -2, -3.
All right.
Right? By the way, can anybody remind me how much data sits between these two values right here? Anybody know that? Anybody know how much data sits inside of here?
25, 50, something like that.
Try it again. How much data sits inside of here?
What is
33%.
Keep guessing.
Isn't it like 67 or 68?
68%. Thank you. It is 68%. Whoever came in and saved the day. This is 68% inside of here, by the way. How much data sits inside of here? Within 2 standard deviations. 95%. Good. 95%. Do y'all remember that?
Yes.
How much data sits within 3 standard deviations?
99.7.
99.7%. 99.7%. Right? So these are estimates, actually. These are estimated values. I'm going to show you in a few how we can actually calculate these true values using Excel. Now, in order to do this, we're going to use z-scores. Z-scores. And z-scores measure the number of standard deviations. A z-score measures the number of standard deviations a value lies below or above the mean. If the value is negative, we are below the mean. If a value is positive, we are above the mean. We're above mu. The variable z is equal to x minus mu divided by sigma. The x is going to tell you where you fall on the curve. You subtract the mean and you divide by sigma. That's going to standardize it. It's going to standardize it for us, all right? So here's how we're going to do, though. We're going to find actual probabilities. And we can use z-scores to do that. Because z-scores measure position, every position or every location on the curve corresponds to a z-score. And it's going to measure what we call a percentile. It's going to measure a percentile. And a percentile is the percentage of values that are up to and below a specified value. If I'm up to and below, that means a percentile always measures the It's always going to measure the left side of the curve. It will always measure the left of something. A score of 0 represents 50% of the data. So that means right here at a mean of 0, or at an x value of 0, or at a, this is actually a z-score, the probability, and this is how we write the statement. This says the probability that z is less than 0. Percentiles mean left, or they mean less than. They mean less than, right? Is less than 0 is equal to 0.5000, or equal to 50%. And again, we know that that's true because at the mean is also the median. And 50% of the data lies at the median. The median itself is a percentile, by the way. The median, this right here represents the median. And the median is what we consider to be the 50th percentile. The median is the 50th percentile. So a z-score is going to actually use that fact right there, that the mean is 50th percentile. And that means that anything to the left of this should have a percentile or percentage that's what? Up to here is 50, right? Anything to the left should have a percentage that's what then?
Less than?
Less than 50%. Anything to the right should have a percentile that's what?
More
Greater.
than?
Greater than. That's how this works, all right? Anything to the left, so anything on this side will be less than 50%. Anything on this side will be greater than 50%. And the reason I'm doing that is because I want you to do, when we start doing these problems, there are ways to check yourself. There are ways to make the answers make sense. And one of the ways is to look at where the values lies in relation to the median. If the values above the median, you should have an answer that's bigger than 50%. If the values below the median, you should have an answer that's less than 50%. All right. So we're going to use these tables first, but we'll probably go to Excel in a few. I don't know why I'm using tables. I feel like maybe your homework might make you use a table. So I'll show you how to use a table to do this. What I do, and this is how I learned it too, is I always sketch curves. Now, do you have to sketch a curve? Not really. But I want you to get in the habit of sketching curves, because what curves do when you sketch a normal curve, they help you see what you're calculating. And by that, there are 3 types of calculations you can make. You can calculate up to a particular value. That is a percentile calculation. These charts right here, this chart right here uses that fact right there. And you notice this right here is telling you that it's measuring the left-hand side. That's what this chart is telling me. Now, so anytime I calculate a left tail type thing, it's called a lower calculation. We're doing left tail. Right tails are called upper calculations. These charts don't give you upper calculations. They only give you lower. Excel will only give you lower as well. That is okay though, because we know how to calculate uppers. We know how to calculate uppers using the complement. So we can always do 1 minus something to get the other side of the curve, is what I'm trying to tell you. So when we do an upper, we're going to always do 1 minus the left tail. 1 minus the left tail will give me the upper. One minus the left tail will give me the upper. And then in between, what you really calculate is you're going to calculate using Excel. You have to do the, let's say that this value right here. I don't want that. This value is Z1. This value is Z2. To calculate this, you have to find the probability of Z2. As Z2 is less than some Z-score, and subtract it from the probability that Z1 is less than some Z-score. And I'll show you how to do that too. All right, so we're going to draw these 3 types of curves. The 3 types of curves we're drawing are to help us actually figure out what we're calculating, the way we're going to calculate it, all right? All right, so this says find the following probabilities using a standard normal table. I have this link or something. I'll show you how to do it through the standard normal in a second. So this first one says find the probability that z is less than negative 0.75. Z is less than negative 0.75. So here's what I do. I want to locate the z-score of negative 0.75. Where does that fall at? Where does less than negative, where does negative 0.75 fall at? In between what two values?
The left.
Negative 1
To the
and
left.
0.
So between negative 1 and 0. So your first value is falling somewhere over here. There's a z-score. And I want to find the area to the left because it's less than. Y'all got that? I want to find the area to the left because it's less than. I just put them in Blackboard. If somebody, whoever was asking about that, it was David. I just put them in Blackboard. They just got uploaded a second ago, actually. Let me put in something else for y'all real quick. If we want to find the area to the left of negative 0.75, this chart is great at finding areas to the left. It's really good at finding areas to the left, all right? So all you have to do is, here's how you read the chart. The z-scores. The z-scores go from 0 all the way up on this one. In this particular chart, it goes all the way up to negative 3.4. And that's because, remember, how many standard deviations are underneath that curve, by the way? How many are to the left of the curve, to the left of the mean?
3.
3, right? So that's why you only need to go up to 3.4. On this particular chart, they go from 0 all the way up to 3.4, but this is positive, right? So what I do first is this. I find the z-score, I find what I'm trying to find, the ones and the tens digits. If y'all know math, ones digits are the number in front of the decimal, and I look at the tenth digit, the tenths, which is the number behind the decimal. So look at the ones and the tenth digits. Well, I'm looking for, right now, I'm looking for z is equal to 0.75. Z is equal to 0.75. Have I showed you how to use this chart before?
No, sir.
No, sir.
Okay, I just want to make sure. So look, negative 0.75, my fault. Negative 0.75. So what I do now is I come on this chart, I'm gonna find the first part. There is a 0 for the ones digit here. There's a 0 here. The tenth is a 7, a negative 7, or 7. So I come here, it's sitting right here. Y'all see that? And then the hundredths is sitting up here at the top. So I want to find a 5. Here's my 5. So when I do this one right here, and this right here, and their intersection is at, so the probability that z is less than negative 0.75 is equal to, it looks like 0.2266.
That's pretty cool.
Yeah, it's this value. I'm glad you feel that way, man. Most people don't say that about statistics, but yeah. Yeah, that's why you read the chart, all right? The chart is read just like that. So you find the 10th digit first, find the ones in the 10th digit first, and then you find the hundreds at the top, all right? So let's look at the next one. So we just said that this one was equal to 0.22, what was it? 0.2266. The next one says find the probability that z is less than 1.3. So again, where does 1.3 fall at? In between what two values? Where does 1.3 fall at?
1 and 2.
1 and 2, right? And I want to be less than that. So which way do I shade? I'm going to shade to the left. So again, my chart is really good at finding this type of probability. It can always find left probabilities with no problem. So when I go to my chart this time I need to look at my positives. Because I'm looking at z equal to 1.30. So again, I'm going to find my ones and my tenths first. So I come on here and I see that 1.3 is sitting here. So I'll draw a line across like that. And then this time my hundredths digit is 0. So I'll look at this up here. And I can see that this is equal to 0.9032. So the probability that Z is less than 1.30 is 0.9032. Now, some of y'all are gonna fall in love with this, and you're going to use the chart for everything. And again, that is cool. I am not a chart fan. I am not a chart fan, but I also like to use calculators. Some of y'all like still counting your fingers. So, I mean, you can do it that way too. You know, it's just your preference. Now, look at these next ones. This one says find the probability that Z is greater than -1. Well, -1, that sits exactly right here. Everybody got that? Everybody saying that? And I'm shading this one which way this time? Left or right?
Right.
Greater than means to the
Wait.
right. So I'm going to shade everything this way. I'm shading everything to the right. That's what greater than is. Everybody got that? If I want to be greater than -1, then here's what has to happen. When I go to my chart, what should I be looking for? What do I look at in my chart?
2 and 2.
I look at -1, right? And so when we do this, if we want to find the probability that Z is greater than -1, here is -1 right here, right? And here's that value. And it's this number right here, which is 0.1587. 0.1587. Everybody see that
So you-
part, right?
So you
that part?
subtract that from 1?
Good. That's what we're going to do eventually. So I wanted you to understand, though, that when I look at this graph, when I look at this particular graph, here's why we graph them. If you tell me this is 0.1587, I automatically know that you're wrong. Why is that? There's at least how much data sitting here? There's at
There's at-
least what?
Over
Mm,
50%.
50%. There's at least 50% because the median's included in here. Do you understand that? That 0.1587 actually represents what?
You have to subtract it from 1, right?
Good, because that 0.1587 is this back here. This is the 0.1587 that you just calculated in the chart. That's that 0.1587. If I want this right here, this is 1 minus 0.1587. Because they have to add up to 1. So I do 1 minus 0.587, 0.1587, and I get this right here, 0.8413. Now, there's a much quicker way to do this rather than doing 1 minus every time. And that's to realize that because these graphs are symmetric, this right here, -1, corresponds to the same thing as +1 on the other side. And watch what happens when I go look at the graph for +1. When I go look at +1, look at what the value is for +1. The value for +1 is what?
The answer that we got.
After we just got by hand. So if I want to find the right-hand side of a curve, I can always do that by flipping the sign of the z-score that they give me. You understand that? So they give me a -1, I need to go look at a +1. If they give me the probability that z is greater than 2.31, well, 2.31 is going to fall somewhere out here, right? And greater than that value, something this way right here. I can do 1 minus whatever I get there. Or what else can I do? What else can I do?
Look at the negative.
Look at the negative version. Because really what you're doing when you look at the negative, well, here's -2.31 sitting out here. What he knows about both these areas?
They're equivalent.
They're the same things. But the chart only gives this left-hand area. The chart literally only gives this left-hand area. It doesn't give this right-hand area. But this right-hand area is the same thing as this left-hand area. So instead of looking at 2.31, what do I go look at?
Negative.
-2.31. So on my chart, remember, I'm looking at -2.31. So here is -2.3. Here is that 0.1 part, that 0.01 of it part right here. That value is 0.104. That value is 0.104. Does that answer make sense?
Is it
Yeah.
0.104 or
It's
is it
0.01. It's 0.014, right? Should have a 0 in front of that, right? Should have a 0. That's what it should be, right? Yeah, 0.0104.
So is it always going to be a positive answer?
Yeah, because it's a probability.
Okay,
That's a
got
great
it.
question. It's a probability, so it always has to be positive. It will always be a positive answer here. Now, here's what happens, and I want you to notice this. The further you move away from zero, the smaller the probability starts to become, depending on what side you're looking at. So we're going to get to eventually. But yeah, it's always a positive answer. The next one says find the probability between -1 and positive, +1. So you're finding the probability between this value and this value. We already know that probability should be approximately what number? We said it should already be what?
68%.
68%. It should be pretty much close to 68%. Here's how we calculate it. If you're calculating between two values, here is Z1 and here is Z2. I find the probability of Z2 first. So the probability of Z2 being less than +1. That's what Z2 is. The probability that Z2 is less than +1. So we need to go to our chart for +1. We already said that's equal to what?
0.8413.
0.8413. That's that. Then I find the probability for Z1, the smaller of the Z scores, is less than -1. We found this probability already too, by the way. That's equal to,
Would
so
it be
-1 is,
greater than?
it's just less than. You always do less than. This one is 0.1587. And what we do to these two probabilities is we subtract them. We subtract those two probabilities. So when I do 0.8413 minus 0.1587, look what I get. That's equal to 0.6826, which is approximately what percentage again?
68%.
It's approximately 68% that the empirical rule gave me. If you did 95%, you would get the exact same thing. That's how this works, all right? Now, that's using the chart. I want to show you how to do this on Excel as well. I want to show you how to do this on Excel, all right? So in Excel, you have a function. In Excel, you have a function called, there's actually two that we can use, but we're going to use the first and standard normal. Norm, you say you have norm.dis and norm.s.dis. Norm.dis is for any normal curve with any mean and any standard deviation. Norm.s.dis is for a standard normal. You're going to give it the z-score and it will always calculate the left side because you're going to type in true. So if we look at our first z-score, which was -0.75. That was that first z-score. And for the word cumulative, where it says cumulative on mine, you do a comma and you're going to type in true. Type in true. And it's going to give you the area to the left of that z-score. What do we get from the chart?
Same thing.
0.2263. That's what we got. So this is more accurate. It's more decimal. The next one was 1.3, right? So again, I do norm, and I'm using this function in particular. Norm dot S dot dis because it talks about a z-score. All right, this only works for the z-scores. So I type in 1.3, 0 for my actual z-score. And again, cumulative will always be true for this.
Okay.
It's always going to be true for this particular distribution.
I was gonna-
Always type that in as true. 0.9032. When we did that a second ago, we got, what did we get? We got 0.9032 as well. All right. And so if you want to do the greater than problems, two ways you can do them. You can go about finding that first one. What was the first one? -1, greater than -1, right? If we want to find greater than -1, I would do this. Because it's greater than -1, I do 1, or let me start the function, equals 1 minus norm.s.dis. It was -1, right?
Yes.
Thank you. -1, cumulative goes to true. Type that in. Here's what you get, 0.84134. Or instead of doing all of that, remember what I just told you? If I want to find greater than -1, what else can I look at on the chart?
Positive.
Positive. If it's greater, then you can always flip the sign and look at that value. So I can do norm.dis. Norm.s.dis. Instead of doing -1, I'm going to do a +1 now. And set this to true. There, true, there. And I get the same thing. So it's just how you like what your preference is, all right? It's really your preference when it comes to doing these type of problems. If you want to use the chart, use the chart. If you want to use Excel, use Excel. All right. Z-scores are going to be, go ahead, I'm listening.
Can you only flip the sign if it's greater than?
Yes, you only flip the sign if it's greater than. That's the only time you flip the sign. If it's less than calculates normal, less than calculates the way we want to calculate it.
Okay.
Greater than doesn't. There is no greater than in terms of this distribution. All right. You can find charts that actually calculate greater than. I'll leave that up to you to find if you want to. Just that know that, like, for instance, if you want to calculate greater than, some charts will show up. You see how on my chart right here, it's telling you that everything you're calculating is to the left. Everything you're calculating here is also to the left. You see that? Some charts you'll see some charts they'll give you this chart right here, and they'll also give you the ones that calculate to the right as well. But the right ones just flip the signs around anyway, so that's all they're doing. All right, so now that we can calculate it with z-scores, here's what's going to happen though. We can also calculate these values now for values that are not z-scores. And that means that normal curves that don't have a mean of 0 and standard deviation of 1. All right. There's two ways we can do it. I'm going to show you both ways, but I'm going to lean on the one way more than the other when we get past this first time, right? The first time I'm going to show you both ways. So here's what we have. It says a customer calling a call center spends an average of 45 minutes on hold during the peak season, the standard deviation of 12 minutes. Suppose these times are normally distributed. This is key. In any one of these problems, it's going to tell you that something is normally distributed. If you see normally distributed, that literally means draw a normal curve. It literally means draw a normal curve. And when to find the probability of the customer being on hold for each interval of time. So what this is literally saying is that we have a variable x. It follows a normal distribution. This symbol right here means follows. X follows a normal distribution with a mean, in this particular case of 45, and a standard deviation of 12. Now, what I'm going to do first then, if I know the mean of the curve is 45, where do I put that 45 at?
Where the line in the middle is.
So I put it in the middle. So the 45 goes here. I want to find the probability of getting a time that is more than 54 minutes. I want the probability of X to be greater than 54. Where does that 54 fall at, right or left of 45?
To the right.
To the right. Fall somewhere over there to the right. We don't really care where it's on the right somewhere. And in particular, what kind of area am I looking for? Left, right, or between?
To the right.
It says more, it's good. It says more than 54. The symbol says greater than. So I'm going to shade to the right of the curve. Shade to the right-hand side like this. Now, one way to do this, one way to do it, and it's perfectly acceptable to do it this way, is to use a z-score. It's how we do a z-score. We can say that z is equal to x minus the mean divided by the standard deviation. X minus the mean divided by the standard deviation. So I can do 54 minus 45, divide that by 12. I get 0.75. So this is equal to 0.75. And what that really means is that if I had this curve on a 0, 1, if I had it on a 0, 1 curve of standard normal, this value right here would correspond to a z-score of 0.75. Y'all got that? That's what that really means. So what I really want you to find is the probability that z is greater than 0.75. The probability that z is greater than 0.75. What does that mean?
1 minus 0.75.
Good, we have to do 1 minus something, right? Or we can look at what?
Negative
We can
0.75.
look at the negative 0.75. Why can I look at a negative? Because what's the sign here? The sign is greater than. So I'm going to look at the negative because I don't do all that work 1 minus. But so we go here, look at negative 0.75. We already found that, by the way. That's equal to what? That's that 0.226. So this is equal to 0.2266. That means that this right here is also equal to 0.2266. All right. That's one way to do it, finding a z-score. You can find a z-score for all these problems, by the way. I don't like to do all that work. So I go straight to Excel when I do it in Excel. And here's how I do it in Excel. For a problem like this, what I'm going to do is I'm going to use a new function. I'm going to use a new function. And the function I'm going to use now is norm.dis. Norm.dis is not for z-scores. Norm.dis takes into account any mean and any standard deviation. So my x here is the value 54. That's the value they're asking me about. My mean was 45. My standard deviation was 12. And my cumulative, what do I set the cumulative to? True. Type that in, press enter. I get this value right here. But again, what side are we calculating?
The
What
right.
side am I calculating? So what do I need to do to that?
Subtract it from
I
one.
do subtract it from 1. So I need to subtract that by 1. So that's 1 minus this. And look what I get, 0.2266 again.
Professor,
So yes, go ahead.
is there any case where the cumulative will be false?
No, not for us.
Okay, thank you.
Yeah, it's always set to true. Always set to true. But notice that you get the same values, right? This way was without the z-score. So it's just dependent on how you want to do it. Just dependent on how you want to do it. And I need you to remember that if you're calculating greater than, it's always 1 minus something, or you can flip the z-score. If you're calculating less than actually use the actual table or actually use the value you get in Excel. You don't have to do anything special with less than. So let's look at the next one. Let's find the probability that is less than 32 minutes. So the probability that X is less than 32 minutes. And again, I mark my mean at 45, right? This value, 32, falls on what side of 45?
The right. I'm sorry, the left.
The left.
The left, good. The 32 is on this side. Which way do I shade, left or right?
The left.
Left.
The left, less than, left, like this. Everybody got that? And so now all I have to do is I can go to Excel, or I can actually calculate the z-score. The z-score for this would be z is equal to 32 minus 45 divided by 12. This is equal to negative 1.08. Do I need to flip the sign when I go to calculate the z-score? Yes or no?
No.
No, because I'm on the left-hand side. Good. So don't flip your signs here. So I go to my chart. Look at that, negative 1.08. So we are first right here at negative 1.0. And we need to come over here to the 8. And it looks like that's equal to 0.1401. 0.1401. It's equal to 0.1401 using the chart and the z-scores. Again, if I go to Excel though, using Excel on this problem, I go equal norm.dis, because it's not z-scores. I don't want to worry about the z-scores. My value was, it was 32, right?
Yeah.
Value was 32. The mean is 45. Standard deviation is 12. Cumulative set to true. Press enter. I get 0.13933. Oh, you know why I get 0.13933 and not 0.140 whatever?
Why?
I was trying to figure out, because the z-score, what was the actual z-score? Our z-score is actually what?
Negative.
Negative 1.08333333. Do y'all see that? The problem with this value right here though is that my chart only reads how many decimals? My chart can only read how many decimals?
4.
2. It can only read, the answers read 4, but the actual chart, the z-scores, only read 2. So that's why when we drew this one, we said negative 1.08. Negative 1.08 falls right here, right? That's negative 1.08. But we should be a little bit more than that. So we should actually be between what two values? We should actually be between these two values, by the way. That's what this is saying. We should actually be between those two values. If we actually did the true z-score, which was negative 1.083, it would put us in between these two values. If you go back to Excel, Excel puts us at 1.3933. Y'all see that? Which is between those two values. Excel is a lot more accurate though. Excel is a lot more accurate because it's actually taking into account, it can actually calculate the extra value. So I'm saying that because here's what's gonna happen on your homework. If MyMathLab asks you to use the table, right? If MyMathLab asks you to round to exactly 4 digits, use Excel. If you do it on a test and you get an answer that's slightly off using the table, go use Excel, all right? Excel is going to be a lot more accurate because Excel can actually calculate those other decimals. We can only calculate up to 2 decimals with a z-score. That's how this works. So unless it's an exact number like that other problem, like unless it's an exact value like this 0.75 was right here, which only has 2 decimals, right? If you don't get something like that, if you get something where, I should write this all the way up. If you get something like this, Excel and the table won't always line up, but Excel is the more accurate answer. All right. The next one, between 32 and 54. between 32 and 54. So again, what we do is mark 45 on this distribution. 32 is here. 54 is here. Right?
Right.
Now, we want to calculate these. So what do you do first? You calculate the probability that X is less than 54 first. Calculate the bigger value first. So if we go to Excel, that's what I'm gonna do this one in. I'm not gonna use z-scores. But I want to find the probability that X is bigger than 54 or less than 54. Norm.dis, 54, 45, 12, true. I get this right here. Right, that's the first one. The other one was 32. I'm gonna calculate that while I'm here too. Norm.dis, 32, 45, 12, true, again. I get this. Final answer is I subtract those two values. That's the final answer. 0.6340. So the probability that X is less than 54 first was 0.7734.
Mhm.
Probability X is less than this is 0.7734. The probability that X was less than 32 was equal to 0.1393. And then I just subtract these two values. And I get 0.6341. Hey, then do y'all have this calculator? Do y'all have graphing calculator TI-84?
How do you get it?
Yes, sir.
I downloaded the calculator. It's called, the calculator I have right now
Mhm.
in the App Store is called trying to find it. I got so many things on my desktop. It's called Graphing Calc 83. Right? And it's a TI emulator basically. But if you have this calculator, it makes calculating these a lot easier, especially the in-between values, because there is a normal function on the calculator, by the way. And so in my high school classes, I use these calculators. So if I do this, there's a normal CDF function, which is the same thing we're doing. Where if you type in this, you get the same answer, 0.634, just like that. So if you want to try experiment with that and you want to get that calculator, I'll put a video up in Blackboard for you. But these go by, they're so much quicker on the calculator than they are in Excel and this, because this calculator can actually calculate, for instance, like we had to go, if I want to find this one right here, I can calculate that one. I calculate that one like that and get 0.2266. And I don't have to do the 1 minus stuff that we're doing right now. Because this calculator can calculate both sides of the curve, actually, can integrate both sides of the curve. So if you want to know how to do that, like I said, you can get the calculator, and I'll put a video up on that too. I don't care if you use it or not. It's just so you have access to it. Y'all go ahead and try this example, please. Go ahead and try this example. All right, I'll give you time to work on this. Go ahead and try it. Knock out. It says birth weights of babies in the United States can be modeled by a normal distribution with the mean of 3,250 grams and a standard deviation of 550 grams. So they already told us that it can be modeled by a normal distribution. What that really means is that we can draw a curve. And we know that the birth weight X follows a normal distribution with a mean of 3250, standard deviation of 550. Those weighing less than 2,500 grams are considered to be of low birth weight. First question, what proportion of babies born are considered to be low birth weight? Label the mean on the graph first at 3250. They told us that low birth weights are 2,500. So what side of the 3250 does that fall on, left or right?
Left.
Left.
Left of over here. So we're somewhere over here, right? That is the 2,500. And we're going to shade it which way, left or right?
Left.
Left, because we're talking about low birth weights. It's all these people this way. So we want to find the probability that X is less than 2,500. You can find a z-score for this, which I'm sure some of y'all might have done. The z-score for this would be -1.36 something, negative 1.36. So if you found that negative 1.36, you go to your chart. I get a value of negative 1.36, 0.0869. Is that what y'all got?
Yes.
1, 2, 3, 4, 5. Yeah, 0.0869. You could have did it like that. If you did it in Excel, again, this is norm.dis. And again, on this one, we don't have to change anything because it's already calculating the left-hand side. Norm.dis, they said 2,500. The mean was 32,550, and the standard deviation was 550. And your cumulative is going to be set to true. Press that. We get 0.08634 again. You got that?
Yes.
So this first one, left tail calculations are very simple because the chart gives us all. Everybody understand that? These are always going to be your easier ones to calculate. That was 0.086. We'll say there 0.086 something. What proportion? What was it?
9.
0.0869 or the 0.089? 0.0869, huh? Thank you.
Yeah.
All right.
Yeah, with the chart it was 9.
Okay, that's fine. What proportion of babies would your model predict is weighing more than 10 pounds? 10 pounds is considered as 4,536 grams at birth. So again, your mean is sitting at 3250. 4,536 is going to sit somewhere out here. And we're greater than that because you're more than 10 pounds. So the probability that X is greater than 4,536. Right? Again, you can find a z-score for this. 4,536 minus 3,250. Divide that by 550. The z-score for this is 2.3. Your actual z-score would be about 2.34.
Okay, Professor,
Yes, ma'am.
we'll stop right there.
Mhm.
So I see that this is 2.34. At this point, if I'm going to the chart, I will go to the negative, right?
Right, because this is greater than problem. That's exactly what you're going to do. Because it's greater than, you flip the sign. So I'm going to look at negative 2.34 for this one. And that is sitting right here. 1, 2, 3, 4. Yeah, 0.0096. So this probability here is 0.0096, or approximately that. Technically, it's we can call it 0.001, 0.01. So about 1%. This rounds to about 1%, right?
Right.
Or I can go to Excel again. In Excel, I just need to remember when I do this, I need to do 1 minus. So in Excel, it'll be equal to 1 minus norm.dis. X is, what was that number?
4,536.
Thank you, 4,536, 4,536. The mean is 3,250. 0. Standard deviation was 5, 5, 0.
True.
And then the cumulative is set to true. Right? Press that. 0.0096 or 0.0091. I mean 0.001 again. You're going 3. So we can do this in Excel. We can do it through the chart. We can do it both ways, right? Now that we can do that, then now that we can find probabilities, the next thing we should be able to do is go backwards. And what I mean by that is I'm going to give you a probability or give you a percentage this time. And I want to know basically what z-score corresponds to it or what x value gave me that, all right? So here's an example. Scores for police training tests are normally distributed. It means I can draw a normal curve with the mean of 50. So I know x is normal with a mean of 50 and a standard deviation of 10. An agency will only hire applicants with scores in the top 10%. What is the lowest score you can earn and still be eligible to be hired by this agency? So I want you to realize this is something different because we're already talking about percentages, top 10%. Where's the mean at on this curve, by the way?
50.
The mean is at 50. If I'm in the top 10%, where am I located at? On the right or the left-hand side of 50?
Right.
I'm on the right.
Far
I'm
right.
somewhere out here. Good. I'm somewhere out here. This represents the top 10%. That is the top 10%. First question I have for you is this. If I try to use my chart, can I use my chart to calculate that? Yes or no?
No.
Yes,
Why
you
not?
can shift your decimals.
So, but what can I actually use this? And this is your good point. That's what we're going to say in a second. But can I use my chart to calculate this value? If I was calculating this area, can I use my chart for this?
Oh no, because you don't
No.
know where it falls.
But you also know that it's to what side? What side is it on?
Right.
The right. It's on the right side. We can't use our chart for the right side calculations. It just so happens though, we're looking for whatever this X value is right here. Well, the top 10% also corresponds. If I look at the left-hand side, how much area is to the left?
90%.
This is the bottom 90%. That is the bottom 90%. All right. And so now what I can do is this, because I know that this is the top 10% and I can find the bottom 90%, I already know what the percentage is. And my chart actually gives me percentages. My chart gives me percentages though, located on the inside right here. Here are your percentages. These are all percentages. So what I'm going to do now is look for the z-score that corresponds to 90%. So this is what we call an inverse. We're going backwards. So what I do now is I go on my chart and I'm looking for 90%. So let me erase this stuff. And in my chart, 90% is located. 90% is located somewhere in between these two values right here. Do y'all see that?
Mm-hmm.
Which one is it closer to?
0.08.
0.08. It's closer to the 0.08 value. So we'll say 90% is located out here. 1.2. We'll say it's about 1.28. That's where 90% is located, about 1.28. So this particular X value corresponds to a z-score of 1.28, which makes sense, by the way. I want you to understand that makes sense. Why does it make sense? If you're at the top 10%, your z-scores are going to be positive or negative to begin with.
Positive.
It should be positive. So it should be bigger than 0, and 1.28 is bigger than 0. So now that I know this, here's what I want to do though. I want to find the X value that corresponds to that 1.28. So when I do this, I would say the z-score I have, I know a z-score form is 1.28 is equal to X minus the mean divided by the standard deviation. So we're working backwards to find X. This is an algebraic equation that you should be able to solve. I say should. Some of y'all are looking at this like, how do I solve this? I want to clear the fraction first, so I multiply both sides by the number 10. Multiply both sides by the number of 10. 10 times 1.28.
12.8?
Yes. That's 12.8. So 12.8 is equal to x minus 50. I want to get x by itself. How do I get x by itself?
Positive
Add
50.
50 on both sides.
Add 50 to both sides. Right? So add 50 to that number. Here's what I get. X is equal to 62.8. X is equal to 62.8. Hey, does this x value of 62.8 make sense? Yes or no?
Yeah.
Yes. Why does it make sense?
Because
It's bigger than what number?
50.
It's bigger than 50 and it's on the right side of the curve, right? Everybody got that? And if you really wanted to, you can go verify that that is the top 10% by going to, let's go to Excel and verify that. I want to calculate top 10%, I'm calculating the right-hand side, right? So I need to do, in Excel, I would do, because it's the right-hand side, I'm going to do 1 minus norm.dis, 1 minus norm.dis, x is 62.8. The mean was 50, standard deviation was 10, cumulative was set to true. Look what I get. I get a value of 0.100273, which is about 10%. So 10% of the data sits above that particular value, 62.8. Now, calculating it that way was a lot of work. And it's a lot of work that I don't want to do, right? There's another way to do it. There's an alternative way to do it, and that's using Excel. Excel actually has a function that can do this type of stuff. Excel has the normal inverse. Has a normal inverse. I don't want this keyboard. I want my regular keyboard. I hate this keyboard. Equals. Start typing in norm. You see norm.inv? Norm.inv. Normal inverse wants a probability. It wants the percentage, but it always wants the percentage to the left. So remember the top 10%, when we look at the top 10%, right? The area to the left was what?
90%.
So we need to type in 0.9 as a decimal. 0.90. It wants a mean. Our mean was 50. Our standard deviation was 10. We type this in and we get 62.8.
So on this one, you don't have to type true?
No,
Okay.
it's calculating it for you already. It's already assuming it's true. 62.8. Which way was quicker and easier? Excel. Normal inverse, when you do inverse functions, Excel will always be the easy way to go. You got that? I would always use Excel if I'm given a percentage and I have to go backwards. So look at the next one. It says that to those officers scoring below the 20th percentile are sent to go undergo additional training. What is the minimum score needed to avoid this training? So again, our mean is at 50, right? 20, the 20th percentile. What side of 50 did that sit on, left or right?
Left.
The left. And the 20th percentile means you're calculating up to and below. So you're already on the left-hand side. Does everybody understand that?
Yeah.
This is the bottom 20th percent, the 20th percentile. I don't need to do anything special with this then. That's already set up like it is.
Right.
So all I have to do is go to Excel. And in Excel, all I'm going to do is type in equals Norm, I'm using the inverse because it's giving me a percentile. Anytime I'm given a percentile, I use inverse. Norm.inv. The left-hand area, if I'm at the 20th percentile, is just 0.2. There is no flipping that type of thing. The mean here is still 50, and the standard deviation is 10. Type that in. If they score 41 point, looks like a 41.6. If you score 41.6 or lower, you will get to avoid, 41.6 or lower, you're going to go to additional training. Does that answer make sense? Does this X value of 41.6 make sense? Yes or no?
Yes.
Yes.
Yes, because it is lower than 50. And again, you can go verify that if you want to by plugging in norm.dis. So are there any questions about normal distributions up to this point? Because all we've done so far is calculate normal probabilities. In our next section, which is the central limit theorem, we're going to further apply this concept. We're going to further apply this concept, right?